Welcome to Electronic Materials. This video is the first part of Chapter 1. Chapter 1 starts out with discussing the atomic structure. A simple classical model to think of atomic structure is to assume that electrons circulate around a positively charged nucleus, which in the case of a hydrogen atom is just a single proton that is circled by one electron on a orbit. So this goes back to the shell model that was developed by Niels Bohr by 1913, and he was inspired by measurements that had been done by that point in time, where the light emission spectrum of hydrogen gas was measured through a prism. So this here shows the experiment. Essentially, you have a glass tube that is filled with hydrogen, and this glass tube has two electrodes that are baked in. So one can apply a voltage across this gas, and if the voltage is high enough, this gas starts ionizing, and then from this excited state of the gas, light is being emitted. And when you put this light through a prism, then the prism splits it up into its constituting colors. And when you do this with hydrogen, in the visible range you get four lines, and these are violet, blue-green, and red. And since these lines are discrete, we need to come up here, or Niels Bohr had to come up with a model that would explain that only certain light energies, light frequencies, light wavelengths are possible when hydrogen goes from an excited state into a ground state or less excited state. And what he came up with is to say, okay, the electrons, they circle around the nucleus on discrete orbits, and each orbit has a different energy. So if an electron would go from an outer orbit to an inner orbit, then energy would be released, and this energy is sent out as a photon, as a light particle of a particular color or frequency. The relationship between the energy of the transition and the frequency or the color of the light is given by the Planck-Einstein relation, which is very simple. It just says the energy of the transition is equal to the Planck constant times the frequency of the light that's being emitted. So the one that I marked here with this violet purple arrow, that's the one that has the highest energy in this Balmer series, right? Because it goes from all the way out here to that second orbit around the nucleus. And so this here is the violet line. If you look at this one here with 434 nanometers, that is the blue-violet line, and that's a little bit a lower energy. So violet light has a higher energy than blue light, and blue light has a higher energy than green, and green higher than red. And so these four transitions, they give us these four emission lines here. A similar thing happens with the ultraviolet and the infrared spectra. The ultraviolet, the Lyman series, they are the transitions that go to the innermost shell. So we have an even larger energy drop from the outer shells to the innermost shell compared to the visible series. And that gives us even higher energy light, and so that's why that's ultraviolet. The Paschen series, on the other hand, emits infrared light, and the reason for that is that we are only dropping to the third orbital from the nucleus, and so these transitions are correspondingly smaller in their energy release, and that's why we get only infrared light. Let's discuss first the nucleus of atoms. In the nucleus you find protons and neutrons. Collectively they are known as nucleons. The neutrons are in between the protons. The protons are positively charged, the neutrons are neutral, and all these nucleons are bonded together by the so-called strong force. The strong force is very strong, but it only acts over very short distances. So this strong force holds everything together against the Coulomb repulsion between the protons. That's why most nuclei are stable, except those that are radioactive. So let's look at carbon. Most of the carbon that you find naturally occurring is carbon-12. So it has an atomic mass of 12. That means it has 6 protons and 6 neutrons. The atomic number of carbon is 6, and that corresponds to the number of protons that are in the carbon nucleus. And so we have 98.89% of all naturally occurring carbon is this type of carbon, carbon-12. We find 2 more types of carbon in nature, carbon-13 and carbon-14. So these 2 carbons still have 6 protons, but they have a different atomic mass, and that means that they have a different number of neutrons. So carbon-13 has 7 neutrons and carbon-14 has 8 neutrons. So these are isotopes of carbon. There's an interesting thing about carbon-14. It is radioactive, and that means that it decays to half of its amount in over 5,715 years. That allows to use carbon-14 for carbon dating, and in carbon dating one uses the ratio between carbon-14 and carbon-12 in a specimen to determine its age. This works by taking advantage of the fact that the radioactive carbon, even though it decays, is constant in the biosphere because it is continuously produced by cosmic radiation. And so when living beings eat carbon, then they incorporate carbon-14 at a constant ratio relative to carbon-12. But after animals die, then the carbon-14 starts decaying because it's not replenished anymore, while carbon-12 remains constant. And so by comparing the ratio in a fossil with the known ratio of living biomatter that we have today, one can estimate the age of the specimen. Now let me talk about the electron shells. Electron shells are numbered with principal quantum numbers. We start out at 1 on the innermost shell, and then we simply number them 1, 2, 3 as we go to the outer shells. These shells also carry names K, L, M, and N sometimes. It turns out that each main shell consists of subshells, and these subshells, they are numbered with the angular orbital momentum quantum numbers, and they range from 0 to n-1. So if we here in shell 3, then we would have the angular orbital momentum quantum numbers 0, 1, and 2 for the 3 subshells. Usually these subshells are actually referred to with these characters S, P, D, and F for 0, 1, 2, and 3. It turns out that each of these subshells can only take a certain number of electrons, and the formula for that is 2 times 2L plus 1. So let's say we have here a p orbital and with the angular orbital momentum quantum number 1. If we put 1 into this formula, we get 2 times 1 plus 1 is 3, times 2 is 6. So we could put 6 electrons on a p orbital. If you put in 0 here, you'll find that one can put only 2 electrons on an s orbital. A d orbital can have 10 electrons and F can have 14. Let's have a look how this works with carbon and phosphorus. I wrote down here the occupation of the orbitals for carbon and phosphorus. Carbon has 6 electrons. That means we can put 2 electrons into the 1s orbital, right? So one writes that here in superscript next to the quantum numbers. And then we can put 2 electrons into the 2s orbital, and the remaining 2 electrons we can put in the 2p. Why do we not put, for example, all of the electrons into the 2p and ignore the 2s? The reason for that is that the orbitals have different energies, and s orbitals typically have a lower energy than a 2p orbital. And since nature is in general in for lowering its energy if possible, we always put the electrons into the lowest available energy levels or orbits that we have here. Okay, let's look at phosphorus. So phosphorus has 15 electrons, right? It has the atomic number 15. And there, of course, we start out like with carbon, 2 in the 1s, 2 in the 2s, but now we max out the 2p shell, so we put in 6, and then the remaining 5 electrons, they go into the third shell, and of course we start out again with the s orbit, with the s shell, and we put in 2 electrons, max that out, and then the remaining 3 go into the 3p subshell. And so we get this configuration here. Now the outermost occupied shell, right, in the case of carbon, that is the second one. In the case of phosphorus, that's the third one. That is called the valence shell. And this valence shell is really the most important shell because it is responsible for chemical reactions that atoms carry out between each other. One more word about the size of atoms. I said earlier that the nucleus is about 10 to the minus 12 meters. The hydrogen atom already is 10 to the minus 10 meters, so it's about 100 times larger than a nucleus. This explains why matter is largely empty. The size is defined by the electron, which has almost no mass in comparison to the nucleus, and all the mass is in the nucleus, and in between we just have vacuum. A couple more things about atomic mass. The atomic mass is concentrated in the nucleus, I just said. Protons and neutrons, they have the same weight, the so-called atomic mass unit, which is 1.66 times 10 to the minus 27 kilograms. That compares with the mass of electrons in a way that the mass of electrons is just 1,000th of the mass of nucleons. So what I said earlier, that the electrons don't really factor in when it comes to mass of atoms, that is clearly visible here. Now, one more thing we need to discuss is the mole. The mole is a SI unit that is really popular with chemists. So what is a mole? A mole is just the number of atoms that we have in 12 grams of carbon. That number is Na, Avogadro's number it's usually called, which is 6.022 times 10 to the 23. You may be wondering, why are we choosing 12 grams of carbon in order to come up with this number? Well, the reason is simple, because 12 is of course the atomic mass of carbon in atomic mass units, but so we just forget about the U here and replace it with a G for gram, and then we have something that we can measure in the lab, and it's easy to remember. So chemists really like the concept of mole, because when they measure out a certain amount of material on the scale in the lab, then they know how many atoms are in there. And if you want to do a stoichiometrically balanced chemical reaction where you need to have the same number of atoms of compound A and compound B to react them properly, then it's really easy to measure them out and then put them together and get a chemical reaction where there are no leftovers. I just started talking about chemical reactions and chemists in the lab. So what better moment than starting talking about bonding and types of solids? So when we think about bonding between two atoms, what we have in mind is that when they are far apart, they need to somehow attract each other and then come together, and then at some point they are bonded. How does this work? Well, between two atoms we have essentially repulsive forces and attractive forces that are competing. The repulsive forces, they cost energy to overcome, while the attractive forces, they result in an energy loss of the system as the atoms approach each other. So these two forces or energies are competing with each other, and in the beginning the attraction has the upper hand because the distance dependence is weaker than that of the repulsion. You see here there's a 12 and here there's only a 6, and that means that the atoms in the beginning attract each other. So as that happens, energy is being released from the system. So you can think of in this energy diagram, they're rolling downhill here. But at the same time now the energy to overcome the repulsion between the two atoms, because they have positive and negative charges in them that start increasingly seeing each other as we get closer. At some point the energy to overcome the repulsion is the same like the energy that is released from the system because of the attraction. And at that point the process stops and the atoms are now sticking together at a certain distance, but they won't get any closer because it would cost a lot of energy to get closer. So that distance at which they find themselves after this process concludes in this potential energy minimum here, that is the bonding radius between them. Let's have a quick look how the attraction and the repulsion come about. We will talk about this in more detail in a few slides. But the reason for the initial attraction are the van der Waals forces between the atoms. Van der Waals forces are attractive forces between dipoles. Now I just said that atoms are neutral because they have the same number of electrons and protons, but if you look from a close distance, of course, you will see the electrons separated spatially from the positive nuclei, and that means that there is a dipole between them, an electrical dipole. And two dipoles, they can attract each other. For example, when they're oriented like this here, then we have here the negative and the positive charges are closer together than the positive charges and the negative charges, and so the force is attractive between these two dipoles. Now when the atoms get really close, then at some point the protons will be so close that they cannot ignore each other anymore, and the electrons the same. And so at that point then we have repulsion. I need to point out at this point that these curves are a little bit of a simplification of the bonding process. Here when the atoms are far apart, it's true, we only have van der Waals interaction, but when the atoms get close together at this bonding radius, then of course it strongly depends on the nature of the atoms, what elements they are, what kind of bonding we really get here, whether it's covalent, ionic or metallic bonding. So let's have a look into what bonding types are out there. The driving mechanism of all bonding is to lower the energy, right? That's what keeps nature going. And if you think, for example, of a combustion engine, you put gasoline and air in, and then the oxygen reacts with the gasoline molecules. And after the bang, you have a bunch of heat that expands the gas volume, and so that drives the piston in the engine. Such exothermal reactions, they are based on lowering the energy between the atoms or molecules that participate in these reactions. Now in general there are three types of such chemical reactions that are based on the formation of three types of chemical bonds. They are shown here. Now which type of bonding occurs between two atoms that are reacting depends on what type of atoms we have. Now if we have metals and non-metals reacting, then typically we get an ionic bond. In this case electrons are transferred from the metal to the non-metal, and that means the non-metal gets negative and the metal gets positive, and so we have two ions that are together here. That's why this is called ionic. A prime example is sodium chloride or salt. If the atoms that are reacting are non-metals, then we typically get covalent bonds. In covalent bonds, electrons are being shared. That makes sense if you think, for example, of diamond. There are carbon atoms reacting with each other, so they have each the same chemical properties, so they have the same strength to attract electrons, and that then encourages them to share the electrons instead of one taking them from the other. The third type, metallic, as the name says, that occurs between metal atoms. And in this case, the electrons of the valence shell are forming an electron gas that permeates the space between the metal ions that are left after the electrons are taken from them. It's important to realize that these types of reactions rarely occur purely, and that one rather needs to think of them as a coordinate system of bonding. And in reality, we have things like ionic bonds with a covalent character or covalent bonds with an ionic character and so forth. This is also referred to as mixed bonding. There's an interesting way to predict what type of chemical reaction occurs between two reacting atoms. This concept is based on electronegativity. Electronegativity is a number that is assigned to each of the elements on the periodic table, which predicts how strong they are in terms of grabbing an electron. And you see here that on the left side of the periodic system, where the metals are, the electronegativity numbers are fairly small, around 1. And on the right end of the periodic system, where the nonmetals are, the electronegativity numbers are fairly large. That means that the nonmetals have a strong ability to take electrons, while the metals here, they are rather good at losing electrons. So when you put a metal in contact with a nonmetal, then you get an ionic bond, because the nonmetal takes the electron from the metal that has a lower electronegativity. If you instead put two nonmetals together, then they have electronegativities that are similar, and that means that we get a covalent bond, because we need to share the electrons if they have a similar strength. Another thing you can see from these electronegativity numbers is how those mixed bonds come about. If you would, for example, form an oxide between two nonmetals, say arsenic oxide, arsenic has a much smaller electronegativity than oxygen. That would mean, while this is still a covalent bond, it would certainly have an ionic character, because the oxygen is stronger in terms of pulling the electrons towards itself than the arsenic. So there would be a covalent bond, but the sharing would be a little bit lopsided towards the oxygen. Let's have a closer look at the three chemical bonding types. Number one is covalent bonding. As I just said, in covalent bonding, electrons are shared between the atoms that are reacting. So let's see here in these examples. If you have two hydrogen atoms, we remember there's only one electron around a proton. And so if they form a hydrogen 2, H2, then those two electrons, they get shared between those two hydrogen atoms. And we can also say now that each of these hydrogen molecules has a full 1s shell, right? An s shell can only have 2 electrons, and so by combining a hydrogen 2 molecule, each of them can say, well, I have 2 electrons in my valence shell. So they lowered the energy considerably because of that, and that makes for a happily stable molecule. A similar thing can happen with fluorine. This is at the other end of the periodic system, right? So we have 7 valence electrons. In essence, each of the fluorines has 1 electron vacancy here that needs to be filled in order to have a full outer shell. And they can achieve this also by bonding together. In essence, they simply share those 2 electrons that are lonely, and that creates a pair. And so each of them now can say, I have a full valence shell. Again, energy lowered, and we have a happily stable molecule. Another example, more interesting now, is carbon dioxide. So here we have 2 oxygen atoms and 1 carbon atom. And the oxygen has 6 valence electrons, the carbon has 4, as we know already. Now that means the carbon needs 4 more electrons to fill the outer shell, while the oxygen atoms each needs 2, and this is achieved by sharing 2 of the carbon electrons with the oxygens. And so we get here 8 electrons in each oxygen outer shell, valence shell, and we have 8 electrons on the carbon and 8 electrons on the second oxygen. A similar thing happens with carbon tetrafluoride. So we have 4 fluorine atoms and 1 carbon atom. So again, each of the fluorine atoms needs 1 electron. The carbon has 4, and so the carbon shares one of its 4 valence electrons with each of the fluorines, while the fluorine shares the lone electron in its outer shell. And that again gives us 5 happy atoms where each has a full outer shell. You may have noticed that all the examples on the previous slides were gas atoms. And in gas atoms, what you have is that once those 2, 3, or 4, or 5 atoms bond together, each of them has a full valence shell, and after that the reaction ends. These atoms don't have any motivation anymore to bond to anything else because they already have a full shell. So let's look at how a solid can come about. A great example for a covalent solid is carbon. Carbon makes many different structures. Perhaps diamond is the most known of them. So let's have a look how diamond comes about. Carbon, as you know now, has 4 valence electrons. So it needs to make at least 4 covalent reactions in order to get 8 electrons going for its valence shell. So if we have only carbon, right, diamond is 100% carbon, there are no other elements participating. If we put 4 carbons around that center carbon, then of course the center carbon can achieve a full shell because it shares one of its lone electrons with one of the lone electrons of the 4 other carbons that are on the outside. But these carbons that are on the outside, of course, they are not satisfied yet because they only have 5 valence electrons. An easy solution for these carbon atoms is to simply bond to even more carbon atoms. So each of those 4 wants to become a center carbon, and that results in an infinite propagation of this crystal structure from carbon to carbon to carbon, and all of them, except the ones that are on the outside of this resulting crystal, have a full valence shell. In the end, we end up with a face-centered cubic crystal lattice for carbon, and the reason that we get this lattice is that these covalent bonds, they are very directional, and because those 4 outer atoms around the center carbon of each of the tetrahedrons that make up the FCC lattice, they want to have as much space as possible between them, and that results in that tetrahedron form that has a 109-degree bonding angle between 3 of those carbons. I just said that carbon is a pretty interesting material, and here you see why. Carbon can form many different solids, and these structures are called carbon allotropes. And what you see here is those that are based on flat sheets of graphene. An interesting question is, how do graphene sheets come about? So we have here a single hexagonally bonded sheet of carbon, a hexagonal lattice, and these sheets are chemically inert, so each carbon atom is fully satisfied in terms of a full valence shell. So how do they do it? Each carbon has only 3 other carbons it bonds to. The trick is that one of the bonds is a double bond. So we have 2 carbons bonded to the center carbon with a regular single bond where 2 electrons are shared, and then the third carbon atom is bonded with this double bond where 2 times 2 electrons are shared. So we have 2 single bonds together forming this double bond. And when this here forms, then of course the outer carbons are still not satisfied, similar to the tetrahedrons that we saw in the diamond. And so they are motivated to form bonds with yet more carbon atoms, and again we form an infinite lattice. The only difference here is that it's not a 3-dimensional lattice, it is a 2-dimensional lattice, so we get these sheets. Like in diamond, the atoms that are on the outside, they are not satisfied chemically because they still would like to bond to more carbons. But let's say we ran out of carbon atoms, and so what can they do? They have two possibilities. They can either form a tube, so then we get a carbon nanotube. There, a lot of them along this tube are satisfied now because they simply bond with the carbon atoms on the other end of the graphene sheet. But at the end, we still have a few carbons that are not satisfied. This can be further alleviated by forming ball-like structures. Here, all the carbons are chemically satisfied. They have full valence shells. These structures are typically called Buckminster fullerenes. The next bonding type I want to discuss is ionic bonding. You know already that ionic bonds are found between metals and nonmetals. A prototypical example is sodium chloride, also known as rock salt. Sodium has 1 electron in its valence shell and chlorine has 7. And if you look at the electronegativities, you find that sodium has 0.93 and chlorine has 3.16. So you have the required large difference in electronegativities that you get an ionic bond. This means that the chlorine can easily take that lone electron that's on the outer shell of the sodium and incorporate it into its valence shell and fill it up to 8. The sodium is also happy, even though it lost an electron, because it ends up also with a full outer shell. And that means that once these two ions are bonded together, they have successfully lowered the energy of the system, and that means this is a stable bond. It's interesting to consider that the formation of the ions in the beginning of this process actually costs energy. The reason for this energy cost is that the atoms are neutral in the beginning, and when you remove or add an electron, that costs energy because you have to either work against the attraction with the positive nucleus when you remove it, or you have to work against the repulsion of the negative electrons when you try to squeeze it in on the chlorine. And one can measure that the amount of energy that this process costs is 1.52 electron volts. After the ions have been created, however, the energy that's being released when they bond together is larger than the energy it costs to form them. This energy is 4.27 electron volts, and that brings us into stable bonds territory on this ionic binding curve because we are in the negative range now. What's keeping the ions apart from each other at the bonding radius of 0.236 nanometers is the Pauli repulsion, which comes from the repulsion between the nuclei and the electrons when the ions are really close together. Therefore, the ionic binding curve has 3 components, 2 that cost energy and 1 that means that energy is being released, and the bond is stable at the lowest point of that binding curve. You may wonder what this electron volt energy unit is. It's simply a convenience for dealing with these very small energy amounts when one talks about individual atoms. The definition is that 1 eV, 1 electron volt, is the energy of 1 electron that was accelerated through a 1 volt potential. It's easy to calculate how many joules this is. E is just the electron charge of 1.602 times 10 to the minus 19 coulomb, and coulomb volt is just joules, and so we end up with that 1 electron volt is 1.602 times 10 to the minus 19 joules. An example is the ionization energy of hydrogen, which is 13.2 electron volts. The last of the 3 chemical bonding types is metallic bonding. You know already that this bonding type happens when metal atoms bond together. In this type of bonding, electrons are also being shared, which makes sense because, again, the atoms that are bonding together have the same electronegativity, so none of them has the power to take an electron from another one, so they have to share them. But they do something very interesting here. Instead of localizing the electrons in between the bonding atoms, the electrons are actually being shed into the crystal lattice and they can move about freely. One usually says they form an electron gas. And that's the foundation for all these great properties of metals like electrical and heat conductivity. The fourth bonding type I want to discuss here is secondary bonding, which is caused by dipole-dipole interaction. This bonding is also called physical bonding since no electrons are transferred and shared. So this is not a chemical bonding type. Here the participating particles already have full valence shells. No electrons change from one to the other or are being shared, but they still attract each other because all particles have dipoles, because they're full of electrons and protons. And the electrons and protons, of course, are not at the same location within molecules or atoms, and this is why we get dipoles. This type of bonding is always present, even if you have chemical reactions occurring. So one can say the secondary bonding is superimposed to the primary chemical bonding. Secondary bonding explains why there is still bonding even if chemical reactions cannot happen. For example, the existence of liquid noble gases can only be explained by secondary bonding. So how does this work? If the dipoles are oriented in a way that the positive ends and negative ends see each other directly, then attraction can occur. If they are oriented in the same direction, then they are repulsing each other. In gases and liquids, the attractive orientation can easily be achieved because the particles can move around and rotate, and so it's easy for gases and liquids to lower their energy that way and form bonds. And that explains why we have liquid and solid forms of atoms and molecules that otherwise would not react with each other. There are basically two types of secondary bonds. One type is bonds between permanent dipoles and the other is bonds between induced dipoles. A prime example of bonding between permanent dipoles is water. Water consists of water molecules, O2 molecules, that are composed of two hydrogens and one oxygen atom, and the hydrogens bond to the oxygen at an angle, and that means that we get a negative polarization at the oxygen end and a positive polarization at the hydrogen end of these molecules, and that is a permanent polarization. These molecules always have this bonding angle, and that means that when these molecules come together, they orient in a way that the negative ends face the positive ends of adjacent molecules, and so they bond together, and that's the reason why we have liquid water, and that we can also freeze water into a solid. Since water is such an important substance, the bonds here in the case of water are called hydrogen bonds. Let's have a look at induced dipole-dipole interaction. When you have two particles next to each other that are without a permanent dipole, if the electrons and the protons in one of them wiggle around a little bit, the particle next to it sees that and it also starts wiggling, and that means that dipoles are being induced from one particle to the other, and they are usually being induced in a way that they lead to attraction, and that enables particles that have no permanent dipole and cannot react with each other to still bond. And prime examples for this mechanism are the noble gases. This here shows the column of noble gases of the periodic table, and on the x-axis here we have the boiling point, and so you can see that from helium to radon the boiling points go up in temperature. The reason for that is that helium is much smaller than radon, and if you have more electrons and protons, then the induced dipoles are stronger, and that means that the forces between the atoms are stronger, and we end up with stronger dipole-dipole bonding, and that means more energy is required to evaporate the substance. Now you know how particles bond. We just learned that there are chemical bonds, that there are secondary bonds, that chemical bonds are much stronger than secondary bonds. I also gave you a number that chemical bonds release energies in a range of a few electron volts. And so the interesting question now is, what does this really mean in terms of the energy that's in particles anyway? When particles are at a temperature that's larger than the absolute zero, then they move around. And you see that here in this little GIF that I put on this slide. And when you form a bond between two of these particles, then this bond has to essentially counteract this motion and keep the particles together against this intrinsic desire to bounce around. And for that, we need to find out what is the energy of each of these particles that's in this box, and then we can compare that with the bond energy, and then we know how stable these bonds are. So before we dive into figuring out that energy of these particles, let me give you first a demonstration. So I turned on this little GIF down here. This is a view through a microscope into a smoke chamber. That's a little glass box that contains smoke. And what you see here is smoke particles, soot particles, that are being constantly hit by air molecules that surrounds them, and you see how they just move around, and that is called Brownian motion. That's inherent in all systems. No matter what you have, a solid, a gas, a liquid, the atoms, the molecules that are in there, they always move around, and they have that tendency to bang on things, and that can break chemical bonds, secondary bonds, depending on the temperature and how strong those bonds are. So now you've seen how gases contain energy just because they are at the temperature. Let's figure out now what this energy is. And we start out asking what is the total energy that is in this box. And what we can measure is, of course, the pressure. And if you think of it, if you pump up your bicycle tire with a manual pump, then in order to put this at a pressure, this tire, you have to put some work in here, and that gives us already a pretty good sign that the pressure inside that tire is a measure of the energy of that air that is in there. So pressure is probably equivalent to the energy, right? The higher the pressure, the more you need to pump. But of course, there is another factor. If you imagine you would pump up a car tire, then it's clear that you would have to work much more to get this car tire to the same pressure that you have in this bicycle tire, simply because the car tire is much bigger. So you need to pump more air in and squeeze it in to get to the desired pressure. And so it seems that the pressure times the volume is probably a measure for the energy that's in the gas that we put into this tire. And we can sort of demonstrate that pressure times volume is indeed the energy that is in the volume, in that gas volume, if we look at the units of pressure and volume. So volume, the unit is cubic meter, cubed. And for pressure, it is force per area, so we have newtons divided by square meter. And if we simplify this to newtons times meters, then we can look up that this is equivalent to joule, and joule is the SI energy unit. So pressure times volume indeed is the energy of the particles that are inside that volume. Okay, so P times the volume is the energy inside the gas volume. Now let's go from here and try to calculate what is the energy of each of those particles that's inside the box. The first question we need to answer, of course, is why do these particles exert a force on the walls of the box? And of course, the answer to that is these particles move at a certain kinetic energy. Essentially, that's what they have. That's their thermal energy that's in them. It's kinetic energy. And they move and move, and then they bounce at some point into the wall of the container, and then they get elastically bounced back until they run into the other end of the container. And so we can say that the momentum change each time they hit the wall is just 2 times their mass times their velocity. And here now in x direction we one-dimensionalized this for simplicity at this point. I just told you that the pressure is force divided by area, F divided by A, and we can say that force is the momentum change divided by the time. So how many times per time the momentum is changing gives us the force. And that we can calculate by expressing the momentum in the x velocity, and we divide it by the time it takes the particle to go to that wall and bounce back and come back to the other wall. And that's just the time between two such momentum changes. And that gives us essentially the rate of the momentum change, and that is equivalent to the force. So when simplifying this term, we get the mass times the velocity in x direction squared divided by the distance between those two walls in x direction. And that is just the force that is applied by one of those particles. If we want to calculate the total pressure on phase A, we need to add up the forces exerted by all of these particles, and that we can do by multiplying the force of each particle by n, and then also using the average force or the average velocity of all these particles. You need to realize that these particles don't have the same energy because they constantly bounce into each other, and so some are gaining energy, others losing it, but the average is constant at a certain temperature. And so if we want to get the pressure that's coming from all of the particles, then we just multiply the average force. We do that by putting the average bar over the squared velocity in x direction. Here now we introduce the area with a squared, and because we already had an a here in the force, we get a cubed, and conveniently that is just the volume. So already we have a formula now that has pressure, volume, and the velocity of individual particles in it. So far we only operated in the x direction, but the volume has of course 3 Cartesian directions, and so we need to go to 3 dimensions now, and the squared velocity is simply the squares of the x, y, and z velocities added up according to the Pythagorean theorem. And since x, y, and z are the same, right, we don't have any preferential direction in this cube, we can say that the velocity squared is just 3 times the velocity in x direction squared. And of course we still have the averages here because we have so many particles in there. With this new expression we can express Vx squared through V squared, but we have to divide it by 3. And so we end up with an expression for the pressure that is just number of particles, mass of the particles times their averaged squared velocity divided by 3 times the volume. And now when we expand this expression by 1/2, then we conveniently get pressure times volume is 2 divided by 3 times the number of particles times 1/2 mv squared. And you may recognize this here as the formula for the kinetic energy. And so bang, we have here now an expression that equates the energy that's in that box, P times V, with 2 divided by 3 times number of particles times their kinetic energy. And that means we are almost there. Now we can express the energy inside the box by the kinetic energies of each of those particles. The final question to be answered is, well, what is the kinetic energy of these particles? We know now that PV is equal to the number of molecules times the energy times a factor, 2 divided by 3, but we still don't know what KE is, the kinetic energy. And there is only one way to find this out, by doing an experiment. And that's where the awesome gas law apparatus comes into play. You see it over here, and of course there are more fancy setups to do more accurate measurements. But with an apparatus like this here, you could basically get a pretty good number for this kinetic energy of a certain gas. And the way this works is you fill in some gas here. The most simple case is to simply have this full of air, and you put this piston at a certain volume. Then you know the volume of the air in there at atmospheric pressure, at whatever altitude you are. And there's also a temperature measurement, right? So maybe also a heater, I don't know. And anyway, you get an idea what the temperature is in your gas, and you can measure the pressure. And so by pushing down now the handle here, you can reduce the volume, increase the pressure, measure the temperature. And with this, if you do this for a few data points, you could figure out how PV depends on the temperature. And it turns out that there is a linear relationship, and that then can be put into a formula by simply introducing a constant. And this constant is known as the universal gas constant. And R is in units of moles. So here in this formula we divide the number of particles divided by Avogadro's number. And as you probably remember from the slide about mole, that is just the number of moles that we have in the cylinder, the number of moles of this gas. This can be expressed as NKT. So essentially we replaced R divided by Avogadro's number with K, and K can be viewed as the universal gas constant for individual molecules, and that we can use to calculate the kinetic energy depending on the temperature. And we do that by using NKT and equating it with PV in its form of 2 divided by 3 times number of particles times the kinetic energy. And by dividing by N here, we end up with kinetic energy equals 3 divided by 2 kT. And the important result here is that just by knowing the temperature and this constant K, which is known as the Boltzmann constant, which comes directly out of this experiment, we can calculate the average kinetic energy of the particles. This formula is a very important result because we know now that the kinetic energy is simply proportional to the temperature. So as long as temperature isn't zero, the particles in any ensemble of particles will have an energy that corresponds to this equation. Okay, I just said that you can always calculate the kinetic energy in an ensemble of particles, be it solid, gas, or whatever, with 3 divided by 2 kT. Unfortunately, this is not entirely true, because it turns out that this formula is only valid for gases that are monoatomic, so really only if you put noble gases into that box we just talked about. And it turns out if you look at a more complicated system like a diatomic gas or a solid, you get different formulas that have a different factor in front of the kT. And it turns out if you would have a diatomic molecule in the box like oxygen or carbon monoxide, the formula really is Ke equals 5 divided by 2 kT, and if you would do it in a solid, you would find out that the formula is 6 divided by 2 kT or 3 kT. And it turns out that how many 1/2s you have in front of the kT depends on the degrees of freedom that each of those molecules or atoms have inside the box. In a diatomic molecule like oxygen or carbon monoxide, we have 2 additional degrees of freedom compared to a monoatomic gas where they can just move in 3 dimensions, but that's about it. Because these molecules, they can rotate, and we have 2 major rotations that contain energy that are perpendicular to the axis that connects the 2 atoms. The rotation along this axis doesn't play a role because there is much less energy in it. And so you can say a 2 atomic gas has 5 degrees of freedom versus a monoatomic gas that only has 3 degrees of freedom. And now when we look at these coefficients here, and we see that the 3 came by introducing the 3 Cartesian directions into our calculations on the previous slides, we can then say that we can assign an energy per degree of freedom, which is just 1/2 kT. So if you have 5 degrees of freedom, it's 5/2 kT. If you have 6 degrees, like in a solid, because here you have three translational and 3 vibrational degrees of freedom, then you have 6 1/2 kT. So this is really the important number, or the important formula that one needs to remember from these calculations, the energy per degree of freedom. Now you know a formula how to calculate the kinetic energy of each of those particles. Let's try to put some numbers to this so you can actually see how bonds really stack up against this thermal energy that's in atoms and molecules and so forth. Let's calculate 1/2 kT at room temperature, which is 300 Kelvin on the Kelvin scale. And so in order to calculate that, we need to look up the Boltzmann constant. Remember, it came out of the experiment, so this is something one just needs to look up. Cannot calculate it in that sense. And we find that it's 8.617 times 10 to the minus 5 electron volts per Kelvin. So I'm using the one that's in electron volt units because that's convenient here, obviously. And we multiply that with 1/2 and then with the temperature, with those 300 Kelvin. And we end up with 0.013 electron volts. So 1/2 kT is just 0.013 electron volts. This actually is a pretty important number if you are in materials. So I would try to memorize this because you can, with this number, very quickly get an idea how stable a process is, or how likely something occurs based on how hot a system is. So now we know what 1/2 kT is in electron volts, and the interesting point now is, how does this compare to the energy that's in bonds? We know already that chemical bonds have a few electron volts, so this is not really such a big challenge at room temperature. This indicates that a lot of materials, if you want to break the chemical bonds, you will have to heat them up so that you get a larger number here, and then this gets bigger, and so it stacks up better against the bond energies. But if you go to secondary bonds, then you'll see that secondary bonds are much closer to this energy, and that explains why water evaporates at room temperature and why it boils at 373.15 Kelvin, and why noble gases are always a gas at room temperature. Remember, water has permanent dipoles, and these hydrogen bonds that form between water molecules, they have an energy of 0.24 electron volts, so it's much smaller than a typical chemical bond. And if you compare this now with 0.013, you see that this is about 20 times larger. But we will see on the following slides that even if the bond energy is higher than kT, we will still have a few atoms or molecules that have an energy that is high enough to actually break their bonds. And that means that water can evaporate at room temperature. and if you heat it up, it starts boiling. When you look at induced dipoles, on the other hand, like you find them in liquid noble gases, then these are much smaller than 0.1 electron volts, and they're very close, or they're actually smaller than the energy per degree of freedom at room temperature, and that explains why the noble gases are all gas at room temperature, and that they have boiling points that are very low. This graph here brings everything in a graphic perspective. Remember, the bond energy is that energy that's being released when the two atoms bond, and this bond energy needs to stack up against 1/2 kT, and if it's significantly larger, then you have a stable molecule, because the atoms can only bounce around in this potential trough here, but they cannot jump out of the entire potential well that is formed by the bond energy. So far, I always talked about the average energy or the average velocity of an ensemble of particles. So here in point 1.5, molecular velocity and energy distribution, we want to examine what are we averaging over when we say we have an average energy of such and such of a bunch of particles. So it turns out one can measure the speed distribution, the velocity distribution in a gas or in an ensemble of particles. And here you see one possible setup that can be used for that. The nice thing about this setup is that you get directly a visible pattern of that energy distribution. The way this works is in an evacuated glass cylinder, we have these rotating disks, and there's an oven that evaporates a metal, and so we get a beam of evaporated metals out of this oven, and that is sent through an aperture, and that creates a beam that hits this first disk, which is a chopper. So there's just this slit in this disk, and as it rotates, we create a chopped beam of metal atoms that then flies to that second disk. And you can imagine, if the atoms have a velocity that is slow, it takes them a long time to get there, so the disk will have rotated further than if they're fast and then they hit the disk at a different spot that comes a little earlier. And so if you run this apparatus for some time, you get a trace on that detector disk that will look like this here. So in the beginning, here you see or this is the end of the trace really, that's the slow molecules or atoms that took a long time to make it over there, and in the beginning of this curve you see the fast molecules depositing, and in between you have those at a medium speed that's close to the average. And what you would always find is that at the ends here, only few particles make it there, while most, so you see here a wider trace, most make it somewhere into the middle. And this distribution here you can visualize through a Maxwell-Boltzmann energy distribution curve. That's the analytical formula, and more about that in a second. And so this distribution here essentially corresponds to this distribution of atoms. And so you see that here in the middle part, you have those average molecules or atoms, and these here are the very slow ones, and these here are the very fast ones. So you see some fast ones, some slow ones, but most of them are sort of average in their energy. What you would also find is, if you change the temperature in the oven, you will get different patterns here, and as the temperature gets higher, the distribution gets wider, and the maximum moves away from the slow molecules end. So you would see that this broader part would shift a little bit further over here towards the fast end of this curve. And of course the trace here would also get a little longer, because it would get more fast molecules. So a really nice experiment that directly corresponds to these Maxwell-Boltzmann energy distribution curves. This here is the analytical expression that describes the Maxwell-Boltzmann energy distribution. It comes about by assuming a few things like 3 degrees of freedom and elastic collisions and so forth. So this is not entirely describing real existing systems, but the end part of the curve, this exponential factor, that is universally applicable. Luckily, this exponential part of the curve is also the most interesting part of the curve because it governs many chemical and physical processes. Once we know the curve for a particular system, it becomes easy to determine how likely a certain reaction requiring an activation energy A becomes. We'll see in chapters 4 and 5 that this exponential component of the Maxwell-Boltzmann distribution governs many processes in semiconductors. So far, I only talked about atoms and molecules, but of course that Boltzmann-Maxwell distribution also applies to electrons. One expression of this fact is that we always have thermal noise in an electronic circuit. So here you see a piece of conductor that has no voltage applied, and the electrons now would move about here because they also have that energy 1/2 kT. In fact, if you think of that electrons are so much lighter than atoms, it should follow that they're also much faster in their motion, and we will actually see later on that they really have a very impressive speed in terms of meters per second because of that 1/2 kT energy that is inherent to them. So when you apply a voltage to this conductor, then you get a current by means of Ohm's law. And then you would have a superposition of this motion and this motion. We will see later that this motion is actually pretty slow, while this here is very fast. But because we generate a drift in one direction, we actually get a current that goes in one direction. So if you would measure the voltage across a conductor that has no voltage applied, then we would see a fluctuation. Very small voltage, of course, but we would see that it fluctuates quite a bit. This is called thermal or Johnson noise. This is the formula for that Johnson noise, and you see here it's square root over 4 kT, of course, always kT, and then times the resistance and times the bandwidth of the circuit. So we see here that the noise voltage is proportional to the square root of kT, and that it also is proportional to the square root over R. So if the resistance is higher in a conductor, then you get more noise. And of course, if the temperature is higher, then the noise goes up too. One example where we find that exponential tail of the Maxwell-Boltzmann distribution is the Arrhenius rate equation. And this equation gives the probability that an energy is higher than a certain activation energy. So in the formula we have the activation energy which is compared to kT in that exponential factor. The example that's shown here is the diffusion of an impurity atom in a crystal, and more about that in a little bit. So if that atom wants to move from this spot in the crystal lattice to this spot, it has to go through a phase where it actually squeezes these two atoms apart so it has enough room to go through. And you can imagine that this process of squeezing the atoms apart costs some energy. And so we have this activation energy that needs to be overcome until the atom can settle again in this next stable spot in the crystal lattice. And this activation energy is essentially that line that you saw already in the Maxwell-Boltzmann curve that then answers the question, how likely does this process become? What's the probability? So if we have a substantial fraction of the particles above this activation energy line, then we can say this process is becoming increasingly likely. This concludes the first part of Chapter 1. Thanks for watching.